Okay, in today's topic, we will briefly go through the first law of thermodynamics and its simplifications for pumps and also for throttling valves. And then we will work through some examples. All right. So for compressors, we have already covered last time. And for pumps, the first law of thermodynamics works just like the compressor and also the turbine, whereby you are able to neglect the heat transfer. That is for sure. The heat transfer is most of the time negligible, yeah, in pumps. Okay, if you have seen maybe simple water pumps, right, in some homes, the pump does not conduct heat into or away from the fluid going through the pump, right? So we can safely assume that Q dot is zero. Now, this is actually applicable to compressors and turbines, right? This equation. For pumps, actually, you could not have the potential energy to be zero. So the potential energy for the last term here is not zero. And you may assume negligible, but some questions because pumps, forces fluid from low elevation to high elevation, right? So information on the height are most of the time given for calculations of pumps, right? So that's why I say it's not zero. It's not because the value is negligible, but rather, in most cases, information on pumps regarding the height where the water is being pumped from um, is going to be available. So you may use the information and utilize this term on the right hand side, okay, the potential energy term. For the kinetic energy, you can neglect it also, but sometimes information are given, so you must know how to handle the calculations of kinetic energy. So, by the way, guys, this potential energy, right? If it were to be considered, right? Well, you all know how the rest works, right? For the power or work done, the pumping power, yeah. In the case of pump, this is a pumping power. Oh, I don't have too much space for that. Let me just shrink this a little. So for pump, right, the W dot is the pumping power. Okay, so the power required to drive the water from a low elevation to a high elevation. Usually, the pump has a pump rating, so that power rating will give you information on the W dot. And then the M dot is the mass flow rate. This one is the normal business, right? And then your H2 and H1 are all enthalpies, right? So this one from tables, okay? Now for unit conversion for velocity, for kinetic energy, you will have to multiply the denominator by 1000. So this is going to be 2000. And then for your potential energy, you will need to divide by 1000. Why? Well, last time you had the kinetic energy in meters squared per second squared, right? Velocity, which is meters per second, when you square it, right? You square it, it becomes square meter over square seconds. And you convert that to kilojoules per kilogram by multiplying 1 over 1000, right? So that is the conversion. So you can look up this conversion online. So the same goes for the potential energy. You will have g, which is gravitational acceleration, which is in meters per second squared, and then you will multiply by z2 minus z1, which is the height in meters. So you will still get square meter over square second, right? And the same business, you have to multiply by 1 over 1000 to convert to kilojoules per kilogram. So this guy will be kilojoules per kilogram. So at the end of the day, you have to divide this term with 1000. Okay, so that is about it for the first law of thermodynamics for pumps. So let's see example 5.61. A pump is used to pump some water. Okay, so water right here is the working fluid, okay, at a mass flow rate of 10 kilograms per second. You see the information is given there, and it's also illustrated in the diagram below. So this 10 kilograms per second comes from this side, which is state 1 from the bottom, 10 kilograms per second. And so it flows from bottom to top. Okay. At entrance point, the pressure is at 1 bar. Okay, so 1 bar means it's 100 kilopascals. So let's convert this right away. P1 is 100 kilopascals. Temperature of 25 degrees Celsius and velocity of 3 meters per second. Okay, all information is there, right? At the exit point, the pressure is 1.5 bar. Let's convert that to 150 kilopascals. Temperature is 30 and velocity is 15 meters per second. And the height is given, okay. Exit point is located 15 meters above the entrance point. So you can say Z1, which is position 1, is at 0 meters, and position 2 is at 15 meters. All right. Finally, we are asked what is the power needed by the pump in kilowatts. Okay, that is the W dot. It's missing a dot there. So we need to know what is W dot. Gravitational acceleration is given as such. So first step is first law, Q dot minus W dot equals M dot. We already say that this is one way in, one way out, so it's just one M dot. So H2, which is H out or H at state 2 minus H1, kinetic energy. And then we will write down the potential energy term. And so, as I said earlier, heat transfer can almost always be neglected for pumps, right? This is 0. And we are asked what is the power of the pump, which is the W dot. So this is in question. This guy can go to the right, so it becomes minus M dot. Okay, so we have canceled this out. M dot is given, H2 can be found, H1 can be found based on the properties given at states 1 and 2, right? So this is from either A4 or A5. Let's see. And then we will have velocity for V2 and V1, and also G and Z2 and Z1. So everything is there, right? So the only thing we need is H2 and H1, and then we are good to go. So step 2 is tables, right? Let's see. So for H1 first, yeah? We have 100 kilopascals and 25 degrees. So let's see from the tables. We got A5, 100 kilopascals, 25 degree. So T set is 99.61 at 100 kilopascals. So we just have 25, which means it is a compressed liquid. And because of that, for compressed liquid, we have to look for A4 table, temperature based table. And at 25 degrees, we have state 1 as compressed liquid. Okay, and thus H1 is, for compressed liquid, is going to be approximated to HF. Okay, and based on table A4, HF is 104.83. Okay, so 25, HF 104.83. Now let's look at H2. H2 is the conditions are 150 kilopascals and 30 degrees centigrade. So let's look at 150 kilopascals in A5. Okay, 150, you have 111 degrees Celsius, but you only have 30, right? So it's definitely a compressed liquid. So y'all going to A4, 35, okay, and HF for 35 is 146.64, okay, 146.64. All right, so we have everything that we need. Let's solve it. Solve. So W dot equals minus, remember we have carried the minus to the right hand side. Mass flow rate is 10. You know what? Let me just write the units. And then H2 minus H1 is 146.64 minus, okay, minus 104.83. And then you have, oh, by the way, this is in kilojoule per kilogram. And then you have V2 squared, which is 15 squared, minus V1 squared, which is 3 squared. You divide by 2000, okay? And then you add on 9.81 times Z2 minus Z1 is 15 minus 0. All right, so this one you have to divide by 1000, okay? So why 1000? Like I said earlier, yeah, the unit conversion would require you to divide it by 1000. Okay, this one is 2000 because initially it was 2 times 1000. Okay, so both of these terms, right, kinetic energy and potential energy, they are initially in meter squared per second squared once you solve it. But meter squared per second squared needs to be converted to kilojoules per kilogram by dividing it with 1000. Okay, so you have to do the same procedure for both kinetic energy and potential energy terms. And for this problem, you will get the pump power as minus 211, more or less, kilojoule per second or kilowatt. All right, so this means 211 watt or kilowatt is being supplied into the system where the fluid flows, right? So that's why you have a negative value here. So hopefully that one makes sense, yeah? Because a pump needs power, right? And the power is exerted on the fluid. And that's why, based on our convention, where positive energy is work done by the fluid, this is the other way around. Work is being done to the fluid by the pump. Okay. All right. The next one device is called the throttling valve. Okay. In the Malay language, it's called alat pendikitan. Okay. What's a throttling device? It's a device that's used to control the flow rate of a fluid. Okay. So you can have it fast, or you can have the fluid moving slow, right? Just by adjusting this valve, right? And then expansion valve reduces fluid pressure drastically. So there are several examples, yeah, of valves, right? You can see valves in air conditioners, right? If air conditioning systems, they have multiple valves to adjust, okay, the fluid temperature, the refrigerant temperature. Yeah, that's why you can feel that the air conditioner, uh, you know, gives out cold air. All right, there is a magical tool which is called the throttling valve, the throttling valve. Okay, so you will see from an example soon how a throttling valve is able to uh, cause a significant temperature drop in a refrigerant. Okay, and that's why you will experience cold airflow. Or in a refrigerator, you will have, you know, cold environment for your food. Okay, so an example, an adjustable valve, a porous plug, a capillary tube. We will look into a capillary tube as an example soon. Now, for expansion valve, it is a device that can have a negligible potential energy, negligible kinetic energy, and also there's no work and there's no heat transfer that occurs in such device. The only thing that is not negligible is the enthalpy, right? And enthalpy is, as you know it from last time, is a mixture of internal energy and the flow energy, which is pressure times the specific volume. Okay, so these two make up enthalpy, and in a lot of cases, although H1 equals H2 seems very simple, you need to analyze it with respect to the internal energy U and the flow energy PV. Okay, so you can have H1 equals H2, all right. H1 and H2, they are all equal, right? They are both equal. But if you look closely, the analysis will be on the internal energy and its trade off with the flow energy. Now, as such, overall enthalpy will not change for each state, but the internal energy and the flow energy will be converted into each other. For example, if you have uh, a larger flow energy at state 2, this will come at the expense of a lower U2, okay, to make sure that U1 plus P1 V1 has the same value. Okay, so for this case, if you have high P2 V2 and low internal energy U2, right, low internal energy, that implies that there is a temperature drop, right, of the fluid, and that means the working fluid is being cooled down. All right, so like I mentioned a lot of times already, right, internal energy, it will gain value if you supply heat to the system, right? You supply heat to the system, the internal energy will increase. Why? All these molecules, they start to jump here and there, they become excited, and the internal energy increases. Okay, internal energy associated with the molecules of steam, water, air, and so on. Okay, you can have refrigerants, you can have whatever of the working fluid, is what I'm saying. For example, let's see this diagram. We have the same H value, 95.47, okay, H1, and 95.47 for H2. But at this side of the throttling valve, okay, meaning on the left side, you have a much higher U1 and a much lower P1 V1. Okay, but when they add up, right? When they add, they will get 95.47. Once the fluid flows through the throttling valve, for example, if we assume that the fluid flows from left to right, then the flow energy, okay, is said to have increased. That means the pressure has increased, Okay, and so we see a reduction in the internal energy. Okay, 88.79, much lower than 94.79. But in overall, when they add up, they will get 95.47. So this is for non-ideal gas. But in the case of ideal gas, okay, the fluid temperature will be constant. Okay, just now we talked about H equals internal energy plus, oopsie, not plus there. H equals internal energy plus the flow energy. This one is for non-ideal gas. Okay, water, liquid refrigerant, and so on. But for ideal gas case, okay, you knew from your ideal gas knowledge that H2 minus H1 equals Cp T2 minus T1, right? And if H is constant, yeah, H is constant, that means H2 equals H1, okay? Then this becomes 0, right? The left hand side becomes 0, okay? 0 equals Cp T2 minus T1. You can safely say Cp is useless there, and T2 is therefore equals to T1. Okay, so we know that enthalpy is a function of temperature in the case of ideal gas. So when enthalpy is constant, then by default, temperature will also be constant. That's another way how to look at it mathematically. Okay. All right. So let's put this into an example, right? So refrigerant. Now, as I said earlier, throttling valves, when you look at air conditioning system, for example, is like ubiquitous. Yeah? It must be there for any AC system. Yeah. Refrigerant 134A enters the capillary tube of a refrigerator. So we have a capillary tube like the one shown earlier. You see here capillary tube. Okay. So it enters 134A enters at P1 is 0.8 megapascals and is throttled. There is a throttling valve somewhere in the middle, okay, to a pressure of 0.12 megapascals. You know what? I'm going to convert every single thing in kilopascals. So let's chop this off. Okay, so this is P1 is 800 kilopascals instead of zero point 0.8 megapascals, and P2 is at 120 kilopascals. All right. Determine the quality of the refrigerant at the final state. That means we can safely say the final state is a mixture, a saturated liquid vapor mixture, right? So, and the the entrance, right? The entrance is a saturated liquid. So this is a saturated liquid, and this is a mixture. Okay, great. So what is X at state 2, and also what is the temperature drop during this process? Okay, temperature drop, that means delta T, which is T2 minus T1. All right, so you need to find T2 and you need to find T1. Now T1 is much easier. You can just look up at A12, table A12 for refrigerant 134A. So you can see from table A12, okay, we have 800 kilopascals and saturated liquid. So the pressure is 800 kilopascals and saturated liquid. So you can just simply read off from the table, the saturation temperature is 31.31 degrees Celsius. So T1 T1 is 31.31 degrees Celsius. Okay, that's good. How about, oh, hang on. We haven't found the H value yet. So for throttling valves, only the H value is of concern. Okay, so H1 is HF, right? Because it's saturated liquid. Okay, so based on table A12, right? Your HF is 95.47 kilojoules per kilogram. So you know compressed liquid, H will be approximated by the saturated fluid, yeah, or saturated liquid's value, which is F. In this case, enthalpy sub FHF. So let's put 95.47 in our worksheet. 95.47, and then this will be equivalent to H2. Now for state 2, well, I forgot this 1 and 2, but it's self-explanatory, right? So for 120 kilopascals, we are somewhere here, and we have HF and Hg values. So let's take 22.49 and HF G. I prefer HFG because you don't need to subtract anything. You can just take this value right away, which is 214.48. Otherwise, you should subtract HF from Hg, which is Hg minus HF. That's one step extra. So it's the same thing. It will still result in 214.48 kilojoules per kilogram. And then X, you can solve X with the following equation. H2 equals HF plus X HFG. So X is basically H2 minus HF over HFG. H2 is equal to H1, right? So you can just plug in 95.47 minus 22.49 divided by 214.48. Okay, so what will we get from that? Let's see. So we have 95.47 to 2.49. Then you divide that with 214.48. Okay, that will give you 0.34. Okay, so about 34% of the refrigerant has evaporated. Okay, that's what it say. And if you look at table A12, okay, since it's a mixture, you can just simply take the saturation temperature as the temperature at state 2. Okay, so 120 corresponds to negative 22.32. So let me just shrink this a little bit. T2 is negative 22.32 degrees Celsius. And so we have, okay, T1, and we also have T2. So we can have the delta T, right? It's final temperature minus initial temperature. Okay, so we have minus 22.32 minus 31.31. Okay, so that will be, I think, around 2 plus 1 is 3, 3 plus 3 is 6, 2 plus 1 is 3, 2 plus 3 is 5. So you will have a temperature difference of negative 53.63. That means the temperature of the fluid or the refrigerant has dropped by 53 degrees approximately, right? That is really, really cold. Okay, so temperature of refrigerant has dropped by 53 degrees Celsius, right? Oh, that is good, right? When you insert this steady state device, what you get is a colder temperature for multiple use, right? You have to chill some, I don't know, food, some other stuff, right? So it's useful for cooling. Okay. So this is the calculation for throttling valve. Yeah. All right. I think that's all for the lesson today. All right. I hope you get something good out of it. Thank you, and I'll see you next time.